Hello everyone, my name is Malik and I am here to give the presentation on my project, and the topic of my project is stroke prediction using H2O and AutoML. And my team members are Fredy, Kiran and Rejul. Introduction. Stroke is a leading cause of death and disability globally. Early prediction can save lives by enabling preventations interventions. What is the goal of the project? The goal of the project is to build an accurate prediction models using H2O AutoML. On the right side we can see the stroke status worldwide: 12.2 million annual stroke cases and 6.5 million annual stroke deaths. Problem statement. What is the problem statement? The manual model selection can be time consuming and error prone. Medical datasets are often imbalanced and require careful handling. Need for automated, scalable and interpretable solutions. On the right side you can see the manual workflow and the AutoML workflow. In the manual workflow you can see data collection, data pre-processing, model selection, model training and model evaluation. Whereas on the AutoML, data collection, data pre-processing, model selection and training is combined into one process, and then the model evaluation. So AutoML works faster as compared to manual ML workflow. Thank you.
So in this slide we're going to be exploring the dataset overview. So basically our dataset is about the stroke prediction. It's the healthcare stroke prediction dataset. So we actually have 12 different features of the dataset, and basically the dataset is like we have a record of 5,000 plus patients. To be exact, we have almost 5,110 records of each individual patients. Now the features we have in the dataset is age, gender, hypertension, heart disease, BMI and glucose level, and the stroke. That's the target variable for which we want to make the prediction. Now in this slide we're going to be talking about the data pre-processing. So the first flow chart we followed was dropping the irrelevant columns. That's basically the ID. So that's something which we don't need. So we dropped the column ID and then we filled the missing values, especially the BMI feature which had a lot of missing values. So we imputed the missing values with mean for all the BMI missing values. Then for feeding the model, it was mandatory to convert all the all the variables to categorical and numerical variables. So we converted the categorical variables to factors so that it's compatible for the H2O model we're going to be using. Now we also checked and handled the imbalance datasets necessarily. So basically there were a few missing values for the ID, and then for a few missing values for the BMI, and as well as the gender. So as I have discussed, the BMI, the ID was irrelevant, so we didn't impute or handle those, we just dropped it. And for the gender we used the mean values. Now speaking about the model, that's the H2O AutoML. That's the model we used. The major advantage of this model is that it's an AI automated model, so that we don't have to be worried about the model accuracy, the prediction score and stuff. So basically it's going to be using multiple models, and then it's going to be automatically giving us the best model results based on the automated AI workflow it has. So H2O AutoML automatically tests multiple algorithms, and the algorithms we have used in this one is the GBM, XGBoost, Deep Learning, GLM and Stack Embedding. Now like I said, it selects the best model based on the performance metrics. That's basically the AUC score, the loss, validation test score, and the RMSE and those kind of things. Now the fun fact about this model is that we don't have to guess about the score and stuff. Like I said, It eliminates the guesswork in the model selection, and it always gives us the best model from all the models that were trained for this project. Training and model selection. We began with an 80-20 training test split to ensure reliable evaluation. The H2O AutoML was run for 120 seconds, automatically testing multiple algorithms and hyperparameters. The leaderboard ranked the top 10 models, and the best performer was the stacked ensemble of all models, achieving the highest AUC of 0.858, indicating strong predictive performance. Evaluation matrices. We evaluated our model using multiple matrices. The ROC curve shows an AUC score of 0.931, indicating strong discrimination between stroke and non-stroke cases. We paid special attention to precision recall and F1 score for the minority class stroke to ensure the model performs well even with class imbalance. The confusion metric shows 230 true positives and 4,672 true negatives, with relatively low false positives and false negatives, reflecting balanced and reliable predictions. Results. Our results show that the stacked ensemble outperformed all individual models across AUC, precision, and recall. It achieved particularly high recall for stroke cases, which is critical in healthcare where a missing positive case can have serious consequences. The model also demonstrated a balanced trade-off between sensitivity and specificity, ensuring both accurate distinction and minimal false alarms.
So on strain, our model was saved as zip file directly from H2O, making it portable and ready for deployment. It can be integrated into web application for hospital to assist doctors in decision making, used for batch processing or large function dataset, or deployed as an API to provide real-time stroke risk prediction. This flexibility allows it to fit into a different healthcare workflow and scale from small clinic to large hospital system. While our model performed well, there are some limitations to note. First, class imbalance in the dataset can bias prediction towards the majority class. Second, since the data comes from a single source, the model may not generalize well to all population or healthcare settings. Finally, to maintain accuracy over time, the model will need periodic retraining with updated data. In conclusion, AutoML allowed us to simplify and speed up the machine learning workflow while still achieving strong predictive accuracy in a short runtime. For future work, we plan to enhance the model by adding more clinical features using larger and more diverse dataset from multiple sources and integrating predictions with health devices for continuous monitoring. So this is basically our site which we indicate like stroke risk predicting AI. Here we have everything like the homepage, project details, Google Slideboard, Google Notebook, and everything. So this is the homepage where if we go down, we also had some reference links and reference for understanding the project. And here we put the dataset details like this is our dataset. If you click on that, we can go to the dataset which we use for our project, and we have the Google Colab link, the Google project link, and also the model link there. And we also put our Trello board link and our Teams link, and where we provided every details like the student ID, student name. And if you go inside, you can see the Google Slide Storyboard where we are presenting the video presentation, which we will upload it later to the Google site. And you can also see the Google Note LM. And we provided our Google Notebook LM, and we also made one video using the Google LM, and it is about the project page. And we uploaded that to YouTube, and we just linked that to the site. You can see that in about the project. And in future works, we had added some the references which we use in our project. And these are the complete outlook of our project and the site. You can see everything which we did in our project, everything. So you can just go through our site. And at last, we would like to thank professor for giving such wonderful opportunity for exploring the subject and exploring the AI and using so many tools. Thank you.